So, welcome to the Math Olympiad program. This is the open seminar of it. If you want to access the actual program, you can go to chinta.com, and there is a Maths Olympiad coming up in the month of July. So you can always go to chinta.com and register for the Maths Olympiad. It's an online Maths Olympiad, so all of you can safely attend from your home. Okay, can safely attend from your home. It is attended by students from over 6 countries all around the world. So that's great as well. Now, the other thing is that these open seminars are designed to help you to prepare for the program. Now, if you are interested to get more resources like this, you can also subscribe to the YouTube channel. All right. So today we will be discussing a little bit of geometry, and it's a very beautiful problem that we will be starting off with. There are 2 segments, each 1 centimeter long, which are marked on the opposite sides of a square of 8 centimeters. So we have a square of 8 centimeters. Here we go. Here is a square of 8 centimeters. And we want to mark 2 segments which are 1 centimeter long. Each of those 2 segments are precisely 1 centimeter long. And what you want to do is you want to join the segments as in the diagram. You're going to join the segments as in the diagram. So here you go. This is the red one, and maybe I can change the color a little bit. This is the green one. So you have a segment which is red, you have another segment which is green. So you want to join these 2 segments, and you want to figure out what is the area of the shaded region. What is the area of the shaded region? So to do that, you have to start with this particular point M. Can anyone guess where is this point M? I mean, you can try to guess it. Can you give me a guess where this point M is in context of this particular square? If you just look at this square, and if you want to ask where this point M is, okay, so Artya Tiwari is saying it's at the center. Sunil Sharma is also saying it's at the center. Okay. So some people are suggesting that this point M is at the center of this square. We have to see. I mean, maybe it is at the center of the square, maybe it is not. How would you really go about that? Is it at the center of the square? Is it even important to be at the center of the square? We don't know. So we will figure it out in a moment. To do that, we don't even need this point M to solve this problem. This is the most interesting and important part. To solve this problem, we don't need the point M to be in the middle of this page, of this square. We don't even need to know the position of the point M. We don't even need to know the position of the point M. Okay, so why is that? Suppose this point is A, and this point is B, and this point is C, this point is D. Now I want to find the area of this shaded region. This is the base. So how many of you know the area formula for a triangle? How many of you know the area formula of a triangle? Do you know how to compute the area formula of a triangle? Okay, so some of you are responding that You know this, okay? Very good, excellent. So the area formula of a triangle is half times base times height. Maybe you have seen this before. Half times base times height, right? So basically, if you have a triangle like this, ABC, and if you drop a perpendicular, let's call that H. Let's call this H. Then the area of the triangle is H times BC times half. Half times B times H, right? Okay, great. Now, I want to find out the area of this red triangle. I want to find out the area of the red triangle. So what I'll do is, I will drop a perpendicular like this. Maybe I can change the color. So MX is the height. MX is the height dropped from the point M on that side of the square BC. MX is the height. And I can extend it on the other side to make it MY, the height. Okay, so remember the sides of the square is 8 centimeters. That's given to you. The side of the square is 8 centimeters. So can anyone tell me what is MX plus MY? What is the value of MX plus MY? If you add MX and MY, what would you get? Okay, so as many of you are rightly pointing out, exactly. So we are seeing both in YouTube, Facebook, we are getting answers. MX plus MY, the length of MX plus the length of 8MY, they add up to 8 centimeters. Excellent. This is intuitively clear because if I zoom in, let me zoom in a little bit. Zoom out a little bit, okay. If I look at MX and MY, then what happens here is that if you join that, that will be parallel and equal to one of the sides of the square. So this is the roughly the reason. It is parallel and equal to one side of the square. Okay, great. Can anyone tell me now what is the area of the red triangle? The area of the red triangle. So I'll just let you write here. Area of the red triangle is half times something times another thing. What is the area of the red triangle? Let me see if any of you are able to give that answer properly. You have to use MX. It's not a value. You cannot say it's 4 centimeter or anything. You have to give the answer using MX, MY, and stuff like that. Think about it. It's not a particular value. Okay, I see that okay, it's not DX, Deepak. Deepak is almost correct. Deepak is almost correct. This is the base. So what is the base? The base is 1. And the height is what? Can anyone tell me what is the height? Avineet is correct. Excellent. It is half times MX. So this is MX. Very good. So 1/2 times 1 is the base, times height. So you have a base which is 1 centimeters, you have height which is MX, and you have half. That's the area of the red triangle. So maybe I can zoom in a little bit. We're back in the actual zoom. Okay, so maybe I can erase this part out. So I will write it here a little bit more clearly. Maybe that helps. That red triangle is half times 1 times mx. Okay, that's the area of the red triangle. What is the area of the green triangle? What is the area of the green triangle? What is the area of the green triangle? Can anyone tell me the area of the green triangle? You have to think about it. So I'll shade the green triangle here. It's right here. What is the area of the green triangle? It's not the same. We don't know. It's okay. Abhineet is giving a correct answer. Excellent. Very good. So you have half times, maybe I can change this. Okay, this is red maybe. It's half times. What is the base? The base is 1. Excellent. Atya is right. So those who are giving me numbers, 4, 2, these numbers are not right. You don't know those numbers are right. You don't know the actual value of mx or my. You don't know that. You have to use my. Okay. So half times 1 times my. So half times 1 times mx and half times 1 times my. Correct? So if you add these two, if you want to add the red and the green, so what do you get? The red plus the green is half times my plus half times mx, right? It's half of my plus half of mx. It's half of my plus half of mx. Or this is same as half of my plus mx. So we already know what is my plus mx. We already know what is my plus mx. Can anyone remind me what was my plus mx? If you remember, my plus mx was something very simple. It is 8 exactly. So this is half times 8, which is 4. Now you have to appreciate the key idea of this particular problem. The key idea, the main idea of this problem is that you do not need to know the length of mx and my. You do not need to know the length of mx and my. You can still do it. You can still do the problem if you do not know the length of mx and my. All you needed to know that my plus mx, that they add up to 8. All you needed to know that my plus mx, they add up to 8. That's everything that you needed to know to solve this problem. So the answer, the final answer is 4 square centimeters. The final answer is 4 square centimeters. It's half of 8. Okay. So in many of the Maths Olympiad level problems, you have to use tricks like this. Or it's not a trick, this is actually a problem solving strategy. You have to use a problem solving strategy like this. You do not know the actual value of these pieces. You do not know the value of the pieces, but maybe when you add the pieces up, you know the value of the total thing. You do not know the value of the pieces, but if you add the things up, you know the value of the actual thing. So the answer, the final answer in this case is 4 centimeters, right? Okay. Now let's move on to this next problem. Well, it says problem 7. Well, it probably shouldn't say that, but anyway. So now we have this. So let's look at this problem. Measures of the angles of a triangle in degrees are three different integers. The measures of the angles of a triangle in degrees are three different integers. What is the minimum possible sum of its smallest and largest angles? What is the minimum possible sum of its smallest and the largest angle? The smallest and the largest angle. You have three. If you have a triangle, and you want to make the angles are measured in degrees, and there are three different integers. The angles are three different integers. What is the minimum possible sum of its largest and the smallest angle? Okay. So many of you are giving responses in the chat, both in YouTube, Facebook, and you are giving responses in the in Zoom in the class. So I'll give you a minute to actually think about it, and I will move to a board which can be used for this purpose. So we will be trying to understand one of the simplest ideas from geometry. Simplest but very important. It's very simple, but it's very important. So what is it? If you have a triangle like this, let's say a triangle ABC. If you have a triangle ABC, what does it mean to add three angles? What does it mean to visually add three angles? So I will be putting this thing in green, I'll be putting this thing in red, and I'll put this one in blue. So when you say add the angles A, B, and C, what is it that you are actually saying? What is it? What do you mean? What is the meaning of the statement add the red, green, and the blue angle? Now you have to understand the fundamental concept here. Let's not rush into the answer. Let's understand what's going on. Okay? So what it means is you take a scissor, you cut the angle A, and you put it beside B. So what you do is you take a scissor, you cut a little portion of angle A, and you turn it and you place it beside angle B. So you have something like this right here. You have something like this right here. You took the angle A. Imagine what I'm saying. This is very, very important. You have to really understand what's going on. So take a minute, take a deep breath, and try to understand what I'm saying here. You want to add the three angles, the green one, the red one, and the blue one. What you want to do is you want to cut the red angle, and you want to move it such that the vertex, so this point A is the vertex, this is the vertex of the angle. You want to match the vertex of A with the vertex of B. Okay. Now what do you want to do with the blue one? What do you want to do with the blue one? Well, you want to do the same thing again. You want to cut this particular angle and place it beside the red angle. So you cut a piece of the angle, you take a scissor, Imagine this like a paper triangle. Imagine this one is like a paper triangle. If this is a paper triangle, if this particular object is a paper triangle, you cut it like this, you turn it, and you place it right there. Okay. Okay, that's great. So if you do that, you have another piece here. So you have placed the red, the green, and the blue angles all side by side. And all of the three angles are three angles of a triangle. So now it was observed, and this is really a fantastic discovery of geometry, that if you are at the point A, if you are standing at the point A, maybe I can make this larger. If you are standing at the point A, let's zoom in a little bit. If you are standing at the point A and you sort of rotate now to this position, then rotate to this position, and finally rotate to this position, then you could have actually walked from A straight to the final, let's call this point, not call it A, let's call it X maybe. Let's call this point X because we have already used A. So you could have just walked from X to X prime. That could have happened. Forget about degrees. Think about this. How wonderful is that discovery? It says that it is not even a little bit tilted. It says it's just at the opposite. If you just sort of half turn it, you reach the opposite end. If you add any three angles, this will not work. If you add any three angles, this will not work. You have to add the angles of a triangle. You have to add the angles of a triangle. If you add the angles of a triangle, then this red, green, and the blue angle will add up to be a half turn. So those who are keeping on saying 180 degree, 180 degree, 180 degree, you don't really need to say this. You can just focus on the thing that is happening here. What is happening here is that after you join these three little pieces, after you are joining these three little pieces, you are exactly coming back to the sort of opposite end of it. The real question is, why? Why does this happen? Why does this add up to this straight angle? Let's call this the straight angle. Why does it add up to be the straight angle? What is the reason? What is the reason that it adds up to the straight angle? That's the main question. Okay. So let's look at this. Why this adds up to the straight angle? What we will do is we will take a straight line like this and run it parallel to BC. Take a straight line like this and run it parallel to BC. Run it parallel to BC. Or we can do something else actually. Let's remove all these little parts. Forget about that. So what are we trying to do now? We want to show that the red, the green, and the blue adds up to one straight line. The red, green, and the blue, these three angles, adds up to one straight line. So how do we show, how do we say that this is really happening? How do we ensure that this is really happening? So what we do is we draw a line that is parallel to AC. Let's draw a line. Maybe I can erase this, trim a little bit. So I've drawn a line that is parallel to AC. This, exactly. So this line, let's call it L. L is parallel to AC. L is parallel to AC. Okay. So the question is, how would you use this parallel line to prove what you want to show? Okay. It's actually very simple. What you notice immediately is this, that there is this blue and this angle right here. So this angle right here, this angle right here is also equal to this blue angle. This angle right here is equal to this blue angle. And this angle right here is equal to this red angle. This angle right here is equal to this red angle. So why is that? Why is that true? The red angle and the red angle down there, the red angle down here is equal to the red angle here, and the blue angle down here is equal to the blue angle here. Why is that true? Well, this is a property of parallel lines. This is actually a property of parallel lines. So I'll just draw it and you will see what I'm saying. The property of parallel lines is like this. If you have a parallel line, two parallel lines like this, then you can, and if you have another third line which is going like that, you can zoom a little bit, then this angle is equal to this one. So this particular angle right here is equal to this one. So these are sometimes known as alternate angles. So alternate angles. So right here, this angle is equal to this one. So this green line is known as the transversal. And this L1 and L2, the two lines here, L1 is parallel to L2. Okay. So what you do is you look for a sort of a Z here. That's how I remember it. You look out for a Z. You look out for a Z. So I should say an inverse Z in some sense. Then these two angles will be equal. So if I come back to the triangle picture, it's like this, that here we have a Z. So that's why this red angle is equal to this red angle. And similarly, we have a Z down here. So we have the white, this blue angle. So this is the Z down here. So this blue angle is equal to the blue angle. So do you see that all of these three angles will add up to this straight angle now? That's how we have devised the parallel lines. That's how we have devised the parallel lines. Okay, so so now that we know that the three angles of a triangle add up to a straight angle, and the straight angle is the straight angle is often referred to as 180 degree because the complete revolution is 360 degree. So if you do a complete revolution, you come back to the same place, then you go 360 degree. If you just want to go halfway down, you go 360 by 2, which is 180 degree. So it's just the opposite side, right? So now what you really want is three integers, A, B, and C, which add up to 180 degree. What is the smallest possible value of such an angle? What is the smallest possible value of such an angle? What is the smallest possible value of such an angle? Okay, obviously, the smallest possible value is A. Smallest possible value is 1. Okay, so if it's 1, all right. What is the largest possible value of an angle? What is the largest possible value of an angle?